January 5, 1943, off Guadalcanal. A Japanese Betty bomber appears at 11,000 feet, closing on the USS Helena at 320 miles per hour. Below deck, gunners manning the 5-inch 38 caliber batteries scramble to load shells, while fire control officers frantically calculate fuse settings. 22 seconds, someone shouts. That's how long their time-fused shells need to reach the bomber's altitude before detonating. The gun crew rams home a shell with the mechanical fuse set to 22 seconds. The weapon fires. The shell screams upward at 2,600 feet per second. 22 seconds later, exactly as designed, the shell explodes. The Betty flies through the airspace 3 seconds and 400 feet away from where the explosion occurred, completely untouched. The gunners reload. Calculate again. This time, 20 seconds. Fire. The shell detonates. The Betty has changed altitude. Another miss. Third attempt. The bomber releases its payload and turns away while the third shell explodes harmlessly behind it. 3 shells fired. 0 hits. This wasn't failure. This was mathematics. And the mathematics of anti-aircraft fire in early 1943 were absolutely devastating for Allied forces. The United States Navy conducted exhaustive analysis of anti-aircraft effectiveness during the first year of the Pacific War. Their findings, compiled in a classified report dated March 19, 1943, revealed a crisis that threatened to undermine the entire surface fleet's ability to defend itself. On average, naval anti-aircraft batteries required 1,133 rounds of 5-inch ammunition to down a single enemy aircraft, 1,133 shells to destroy one plane. Each 5-inch shell weighed 54 pounds. Each shell cost the equivalent of $400 in current terms. That meant the Navy was spending roughly $450,000 in ammunition alone for every enemy aircraft destroyed, assuming the ship survived long enough to fire that many rounds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't the guns. American 5-inch 38 caliber dual-purpose weapons were engineering marvels, capable of firing 22 rounds per minute to altitudes exceeding 37,000 feet. The problem wasn't the gunners. American crews trained extensively, drilling on loading procedures until they could service their weapons in darkness during rough seas. The problem was the fundamental impossibility of hitting a moving target in 3-dimensional space with a shell that exploded at a predetermined time. Every anti-aircraft shell fired in 1942 and early 1943 used mechanical time fuses. These devices, refined over decades, worked through clockwork precision. A gunner, or fire control officer, calculated how many seconds the shell needed to reach the target's altitude. He set a mechanical timer on the fuse to that precise interval. The shell fired. The timer counted down. At exactly the preset moment, the fuse triggered the explosive charge. The system had one catastrophic weakness. It assumed the target would still be there when the shell arrived. Aircraft weren't cooperative. A bomber, traveling at 300 miles per hour, covered 440 feet every second. During the typical flight time of a 5-inch shell reaching 20,000 feet, roughly 14 seconds, that bomber moved over 6,000 feet, more than a mile. Even if the fire control officer calculated the perfect intercept point and set the fuse perfectly, the pilot could climb, dive, or turn, and the shell would detonate in empty air. The statistics exposed the magnitude of failure. During the Battle of the Coral Sea in May 1942, American ships fired over 4,000 anti-aircraft rounds. They claimed 9 Japanese aircraft destroyed, though post-war analysis suggested the actual number was closer to 5. That represented approximately 800 rounds per kill, and that engagement occurred under relatively favorable conditions with clear visibility and approaching aircraft at medium altitude. Kamikaze attacks created even worse ratios. A determined pilot flying directly at a ship presented the most difficult targeting scenario. The aircraft's altitude changed rapidly as it dove. Its speed increased from the acceleration, and critically, the pilot wasn't trying to survive. He was trying to reach the ship before being destroyed. Traditional doctrine held that anti-aircraft fire would force enemy bombers to break off their attacks or at minimum disrupt their accuracy. Kamikaze pilots couldn't be disrupted. They flew through barrage fire that would have scattered conventional bombers. The only way to stop them was direct destruction, and time-fused shells couldn't achieve that reliably. The Navy's predicament worsened throughout 1942 as Japanese tactics evolved. Early in the war, Japanese bombers approached at high altitude in formation, believing their altitude provided safety. American fighters and improving radar-directed fire taught them otherwise. By late 1942, Japanese pilots adopted low-level approaches, coming in below radar coverage at wave-top height before pulling up for final attack runs. This tactic compressed the time available for anti-aircraft fire from minutes to seconds. A Betty bomber approaching at 200 feet altitude, traveling 400 miles per hour, gave defending gunners perhaps 15 seconds from detection to impact. Setting mechanical fuses, loading, aiming, and firing required most of that time. Ships usually managed 2, maybe 3 shots before the bomber reached release point. The human cost manifested in burning ships and drowned sailors. During the naval battle of Guadalcanal in November 1942, Japanese aircraft damaged or sank multiple American vessels despite intense anti-aircraft fire. The USS Juno took a torpedo hit and later exploded when struck by a Japanese submarine, killing 687 men, including all 5 Sullivan brothers. The USS Atlanta suffered extensive damage from both surface action and air attack. Over 3 days of fighting, American anti-aircraft batteries fired thousands of shells, while Japanese aircraft pressed home attacks that changed the strategic situation in the South Pacific. Commanders recognized they faced a technological problem requiring a technological solution. Mechanical time fuses, regardless of how precisely manufactured or carefully set, couldn't adapt to target behavior. What the Navy needed was a fuse that made its own decision about when to detonate, a fuse that could sense when it had reached the proper position, relative to the target, and trigger itself automatically. The concept wasn't new. Engineers had fantasized about proximity-activated weapons for decades. The theoretical advantages were obvious. A shell that detonated automatically near an aircraft would compensate for every targeting error. Miscalculate altitude by 500 feet, the proximity fuse would still detonate when it passed the aircraft. Target changes course during shell flight, the fuse would sense the aircraft regardless of where it maneuvered. Pilot takes evasive action. Useless if the shell exploded the moment it came within lethal radius. But theory and implementation existed in different universes. Building a device that could survive the violent acceleration of gun firing, remain functional during supersonic flight through thin air at extreme altitude, detect an aircraft from sufficient distance, and trigger a detonation at exactly the right moment required, solving multiple engineering problems simultaneously. The forces involved seemed almost deliberately designed to prevent success. A 5-inch shell experienced acceleration exceeding 20,000 times Earth's gravity when fired. 20,000 Gs. Engineers expressed this force in concrete terms. Imagine every component of a delicate electronic device suddenly weighing 20,000 times its normal weight for the microseconds during barrel travel. Vacuum tubes, the only electronic technology available in 1942, capable of the required sensitivity, shattered under far gentler treatment. The idea of building a vacuum tube that could withstand gun forces seemed absurd. Even if the device survived firing, it had to function in an environment hostile to electronics. The shell rotated at over 500 revolutions per second for gyroscopic stability. It traveled through air at temperatures ranging from -60 degrees Fahrenheit at high altitude to over 100 degrees near sea level. It needed to detect aircraft through variations in atmospheric density, weather conditions, and the electromagnetic interference generated by its own gun's fire control radar. Then came the power problem. The device needed electrical current to operate, but batteries heavy enough to provide adequate power exceeded weight limitations. The entire fuse assembly had to fit within the standard shell nose, replacing the existing mechanical fuse without requiring modifications to millions of existing shells or hundreds of thousands of artillery pieces already in service. Every additional ounce in the fuse meant less explosive in the warhead, reducing the weapon's lethality even if the fuse worked perfectly. The detection problem presented its own nightmare. An aircraft needed to be distinguished from clouds, rain, the ocean surface below, friendly aircraft, and random atmospheric effects. The fuse had to remain dormant during the first seconds after firing to prevent premature detonation from detecting the launching ship itself. It needed to arm itself automatically after safe separation, and critically, it had to make the detonation decision within microseconds once an aircraft entered the lethal radius, because at closing speeds exceeding 1,000 feet per second, hesitation meant the shell would pass the target before exploding. Multiple research teams had attempted proximity fuses during the 1930s. British engineers experimented with acoustic detection, building fuses that listened for engine noise. The concept failed because wind noise during shell flight overwhelmed any aircraft sounds. German researchers investigated photoelectric cells that detected light reflected from aircraft surfaces. This approach fell apart at night and proved unreliable even in daylight due to variations in aircraft finish and atmospheric conditions. American efforts before Pearl Harbor produced similarly disappointing results. The National Defense Research Committee, established in June 1940, included proximity fuse development in its original charter. Section T, headed by physicist Merle Tuve, received responsibility for the project. Tuve's team at the Department of Terrestrial Magnetism, part of the Carnegie Institution in Washington, began systematic investigation of potential detection methods. They quickly eliminated most options. Acoustic detection couldn't work due to flight noise. Optical detection required clear weather and daylight. Magnetic detection lacked sufficient range and sensitivity. That left radio frequency detection, essentially building a miniature radar into each shell. The concept offered promise. Radio waves could detect aircraft in any weather condition, day or night. The technology already existed in larger form as ship and ground-based radar systems, but miniaturization presented extraordinary challenges. A typical radar installation in 1942 occupied an entire room, required external power generators, employed multiple operators, and needed frequent maintenance. Tuve's team had to compress this capability into a package 3 inches in diameter, 5 inches long, weighing under 4 pounds, that would function without maintenance from manufacture through storage, through firing, through detonation, all while costing little enough for mass production. The work proceeded with desperate urgency after Pearl Harbor. Military planners recognized that American naval superiority in the Pacific depended on protecting carriers and their escorts from Japanese air attack. Every day without an effective proximity fuse meant more ships damaged or sunk, more sailors killed, more Japanese aircraft surviving to attack again. January 1942 brought the first breakthrough. Tuve's team successfully tested a radio proximity fuse that survived firing from a ground-based 3-inch gun and functioned correctly, detecting a test drone and triggering detonation. The device worked. The question was whether it could be manufactured in sufficient quantities with adequate reliability to matter in actual combat. The engineering solution that emerged represented collective brilliance from researchers across multiple institutions. The Applied Physics Laboratory at Johns Hopkins University contributed miniaturized vacuum tube designs specifically engineered to survive gun forces. Engineers developed tubes with reinforced filaments, ruggedized envelopes, and special mounting systems that distributed acceleration loads. These tubes, designated as the WW series, could withstand over 20,000 Gs repeatedly during testing. Western Electric provided manufacturing expertise, designing production lines that could build proximity fuses by the thousands. The fuse required 24 separate vacuum tubes, each one hand-assembled with precision matching the finest laboratory equipment. Yet Western Electric's engineers developed processes that allowed semi-skilled workers to produce reliable units at scale. By mid-1942, production capacity reached 1,000 fuses daily and climbing. The fuse's operating principle was elegant. A small radio transmitter broadcast a continuous signal from the shell nose. This signal, transmitted at a carefully selected frequency, travelled outward in all directions. When the signal encountered a large metal object, specifically an aircraft, it reflected back to the shell. A receiver circuit in the fuse detected this reflected signal. As the shell approached the aircraft, the reflected signal grew stronger. When signal strength reached a predetermined threshold, indicating the shell had entered the lethal radius, the fuse triggered detonation. The system included multiple safety features developed through painful trial and error. The fuse remained mechanically locked during handling and loading, preventing accidental triggering. Centrifugal force from the shell's rotation armed the fuse approximately 200 yards, downrange from the launching ship, far enough to ensure the fuse wouldn't detect and detonate near the ship itself. A backup timer disarmed the fuse after a preset interval, typically 45 seconds, causing any unfired shell to self-destruct rather than falling back to Earth as unexploded ordnance. Testing revealed capabilities that exceeded initial expectations. The fuse could detect aircraft at ranges up to 70 feet, creating a lethal sphere around the shell's flight path. Any aircraft passing within that radius triggered detonation even if the shell missed by significant margins. This transformed anti-aircraft fire from a precision targeting problem into an area effect weapon. Gunners no longer needed to predict exactly where the aircraft would be. They simply needed to get the shell reasonably close, and the fuse handled the rest. The Navy conducted comparative trials during summer 1942 at the Naval Proving Ground in Dahlgren, Virginia. Crews fired conventional time-fused shells at radio-controlled target drones, establishing baseline hit rates. Then they fired proximity-fused shells at identical targets under identical conditions. The results seemed almost impossible. Conventional time-fused shells achieved approximately 2% effectiveness against maneuvering drones, 2 hits per 100 rounds fired. Proximity-fused shells achieved 31% effectiveness, 31 hits per 100 rounds. The proximity fuse had increased anti-aircraft effectiveness by a factor of 15. Military officials reviewing the test data initially suspected errors in measurement. They ordered the trials repeated with independent observers and more rigorous documentation. The second round of tests in August 1942 produced nearly identical results. The proximity fuse worked. More importantly, it worked reliably enough for combat deployment. Security concerns immediately dominated. Planning discussions. The fuse represented such a significant technological advantage that its compromise to enemy forces could shift the strategic balance. German or Japanese engineers examining a captured proximity fuse could potentially reverse engineer the technology, eliminating American advantage while creating new threats. A proximity-fused German 88mm shell would devastate Allied bomber formations. Japanese proximity fuses would make kamikaze defense even more difficult than it already was. The Navy implemented unprecedented security measures. Production workers received minimal information about what they were building. Each factory produced only specific components, with final assembly occurring at secure facilities where complete fuses came together for the first time. The fuse received the cryptic designation VT, which officially meant variable time, to disguise its true function. Workers and even most military personnel believed they were building an improved mechanical time fuse with adjustable settings, not a revolutionary radio-guided proximity device. Combat deployment required careful planning to minimize capture risk. The Navy decided proximity fuses would only be used over water, where unexploded rounds would sink rather than falling on land where enemy forces might recover them. Initial combat use would occur in the Pacific Theater against Japanese forces, whose technical intelligence capabilities were considered less sophisticated than Germany's. And critically, ships would only fire proximity-fused ammunition when absolutely necessary, during actual enemy attack, rather than during routine patrol or training. The first combat use occurred on January 5, 1943. The USS Helena, a light cruiser operating off Guadalcanal, detected incoming Japanese aircraft during the evening patrol. The cruiser's 5-inch batteries loaded proximity-fused shells and opened fire as the Betty bomber approached. The first shell detonated 40 feet from the aircraft, shredding its wing with fragmentation. The bomber tumbled into the ocean, marking the proximity fuse's first confirmed kill. The Helena's gunnery officer, Lieutenant Commander Robert Hale, filed a combat report that reached Washington within days. His assessment was direct. The new ammunition performed beyond expectations. Where we previously required an average of 1,200 rounds per aircraft destroyed, tonight we achieved destruction with 4 rounds fired. Request immediate resupply of VT ammunition. Word spread through the Pacific Fleet with extraordinary speed. Captains who'd received initial allocations of proximity-fused ammunition reported similar results. The USS Montpelier claimed 3 Japanese aircraft destroyed with 17 rounds fired during a night action off New Georgia. The USS Birmingham downed 2 torpedo bombers with 11 rounds during a dawn attack. Ship after ship reported the same transformation. Anti-aircraft fire had suddenly become devastatingly effective. The statistical impact appeared in fleet-wide analysis compiled during March 1943. Ships equipped with proximity-fused ammunition were downing enemy aircraft at rates 4 to 5 times higher than ships using conventional time-fused rounds. The average ammunition expenditure per kill had dropped from over 1,000 rounds to approximately 250 rounds. That meant the same ammunition supply could stop 4 times as many attacks, or alternatively, ships needed to carry far less ammunition to achieve the same defensive capability. The psychological impact on Japanese pilots proved equally significant. Bomber crews accustomed to flying through anti-aircraft fire that detonated predictably at set altitudes suddenly encountered shells that exploded seemingly at random whenever aircraft came near. The unpredictability destroyed standard evasive tactics. Pilots couldn't time their maneuvers to slip between barrage patterns because there were no patterns. Every shell became a potential kill because every shell detonated at the optimal moment. Japanese after-action reports captured by American intelligence revealed confusion and fear. One document, translated in April 1943, described American anti-aircraft fire as having greatly improved accuracy through unknown means. Another report noted that enemy shells now detonate with uncanny precision near our aircraft regardless of altitude changes or evasive action. Japanese commanders had no explanation for why American anti-aircraft effectiveness had suddenly quadrupled. The Battle of the Philippine Sea in June 1944 demonstrated the proximity fuse's strategic importance. American carriers faced the largest Japanese air attack of the war, over 300 aircraft in multiple waves attempting to destroy Task Force 58. American fighters intercepted most attackers, but dozens broke through to face the DAR, fleet's anti-aircraft defenses. The ships opened fire with proximity-fused shells. The results became known as the Great Marianas Turkey Shoot. American anti-aircraft fire destroyed over 60 Japanese aircraft, while friendly fighters accounted for most remaining kills. Of the 300 aircraft that attacked, fewer than 30 survived. Japanese carrier aviation never recovered from losses suffered that day. Losses inflicted partly through proximity-fused technology the attackers never understood. Fleet Admiral Chester Nimitz, commanding Pacific operations, submitted a classified assessment in July 1944 that stated, "The VT fuse has proven to be the most important anti-aircraft development of the war. Enemy air attack effectiveness has been reduced by an estimated 70% due entirely to this single technological advancement. I cannot overstate its value to fleet survival." Production ramped up dramatically through 1943 and into 1944. Western Electric's manufacturing plants in New Jersey and Illinois produced proximity fuses around the clock. By mid-1944, Monthly output exceeded 200,000 units. Every major combatant ship in the Pacific Fleet carried proximity-fused ammunition for its 5-inch batteries. Smaller vessels and auxiliaries received allocations based on threat assessment and mission requirements. The manufacturing achievement deserves recognition alongside the engineering triumph. Each proximity fuse contained 24 vacuum tubes, multiple resistors, capacitors, batteries, and mechanical components, all assembled to tolerances measured in thousandths of an inch. The production line had to produce units reliable enough that military commanders would trust their ship's survival to devices built by workers who didn't fully understand what they were making. Quality control procedures rivaled anything in American industry. Every fuse underwent multiple inspections during assembly. Random samples from each production batch were subjected to live-fire testing, actually fired from guns to verify they would survive acceleration and function correctly. Fuses that failed inspection were disassembled, studied to determine failure modes, and the production process adjusted to eliminate whatever had caused the problem. The cost per unit dropped as production scaled. Early proximity fuses cost approximately $18 each, expensive but justifiable given their effectiveness. By late 1944, mass production reduced costs to roughly $10 per unit, only marginally more expensive than conventional mechanical fuses. The economic equation became overwhelmingly favorable. Spending an extra $8 per shell to achieve 4 times the effectiveness meant spending 1/4 as much ammunition to achieve the same result. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. European theatre deployment began in December 1944 during the Battle of the Bulge. German forces launched their final major offensive in the West, and the Luftwaffe made rare appearances in daylight attempting to support ground operations. American anti-aircraft batteries, recently equipped with proximity fuses, engaged German aircraft with devastating results. The guns tore apart German formations that had grown accustomed to Allied anti-aircraft fire being dangerous but manageable. Luftwaffe pilots reported the same confusion Japanese aviators had experienced. Shells that exploded at precisely the wrong moment for the aircraft and precisely the right moment for the defenders. German intelligence eventually determined that Americans had deployed some form of improved fuse, but they never successfully recovered an intact example for analysis. The European deployment carried additional risk because shells fired over land might fail to detonate and fall where German forces could recover them. The army accepted this risk because German air attacks had become sufficiently rare that each engagement mattered enormously. Allied air superiority depended partly on ensuring that the few remaining Luftwaffe aircraft couldn't operate effectively even in their own airspace. Artillery applications expanded the proximity fuse's impact beyond anti-aircraft use. Engineers recognized that a fuse designed to detect aircraft could also detect ground. A proximity fuse set to detonate 20 feet above terrain created an airburst that showered targets with fragmentation from above, defeating trenches and foxholes that protected against ground-level explosions. Field artillery units received modified proximity fuses during winter 1944. The VT fuse transformed conventional artillery into a weapon that could strike enemy infantry positions with unprecedented lethality. German soldiers who survived proximity-fused artillery barrages described the experience as terrifying. Shells that exploded overhead, rather than impacting ground, produced casualty rates 2 to 3 times higher than conventional artillery. The Battle of the Bulge saw extensive use of proximity-fused artillery. American gunners fired thousands of rounds at German concentrations, achieving results that stunned both sides. A single proximity-fused shell bursting over a German infantry company could inflict casualties equivalent to 5 or 6 conventional shells. The German offensive, already struggling against fuel shortages and Allied air attacks, faced artillery fire more lethal than anything previously encountered. Post-war German officer interrogations revealed the psychological impact. One captured major stated, "The American artillery became impossible to survive. We could dig deep foxholes and survive conventional barrage fire by taking cover during bombardment. But their new shells exploded above ground, and there was no protection. My company lost 60% casualties from artillery alone during 3 days of fighting. The technological race never materialized. Despite extensive German research into proximity fuses, they never successfully developed a combat-ready system. German scientists understood the principles and made several prototype attempts, but they couldn't solve the miniaturization and ruggedization challenges. Their proximity fuse projects remained laboratory curiosities, while American fuses destroyed thousands of aircraft and killed tens of thousands of soldiers. Japanese research into proximity fuses was virtually non-existent. Japan's electronics industry lacked the manufacturing infrastructure and technical expertise required for such sophisticated devices. Japanese engineers examining captured American radar sets could barely comprehend how such complex equipment functioned, let alone replicate it in miniaturized form. The proximity fuse remained an inexplicable mystery that made American anti-aircraft fire incomprehensibly deadly. Soviet forces received substantial Lend-Lease aid from the United States, but proximity fuses were explicitly excluded from transfers. American security concerns about Soviet technical intelligence capabilities and potential post-war competition meant that proximity fuse technology remained classified even from allies. Soviet anti-aircraft forces continued using conventional time-fused ammunition throughout the war, achieving far lower effectiveness than comparable American units. The production statistics tell a story of industrial mobilization, matched by few other weapons programs. From initial prototype in January 1942 to first combat use 12 months later, the proximity fuse program compressed development, testing, and production scaling into a timeframe that seemed impossible. By war's end, American industry had produced over 22 million proximity fuses, each one a miniature marvel of vacuum tube electronics manufactured by workers who thought they were building mechanical timers. The human stories behind the statistics reveal the program's true impact. The crew of the USS Helena, attacked by 22 kamikaze aircraft during a single engagement off Okinawa in April 1945, survived partly because their 5-inch guns firing proximity-fused shells destroyed multiple attackers before they could reach the ship. The Helena took severe damage from several kamikazes that broke through, but the ship survived, and most of her crew lived to sail home. Compare that to ships attacked during 1942 before proximity fuses entered service. The USS Lexington sunk at Coral Sea, the USS Yorktown sunk at Midway, the USS Hornet sunk at Santa Cruz. These carriers and dozens of other vessels fell to air attacks that overwhelmed their anti-aircraft defenses. How many might have survived if proximity fuses had been available 6 months earlier? The question haunts the historical record. Individual sailors owed their lives to vacuum tubes and radio waves they never saw. A gunner's mate aboard a destroyer off Saipan, loading proximity-fused shells into his 5-inch mount, probably never knew that each round he rammed home contained technology that increased his ship's survival chances by several 100%. He just knew the shells worked, that enemy aircraft exploded when the ship fired, and that he might actually make it home to his family in Iowa. The technical achievement deserves emphasis. The WWII vacuum tubes that made the proximity fuse possible represented the absolute cutting edge of 1940s electronics. These tubes survived acceleration that would destroy modern solid-state electronics. They functioned reliably in temperature extremes from Arctic cold to tropical heat. They operated correctly at altitudes where air pressure dropped to a fraction of sea level, and they did all this while costing approximately 40 cents each to manufacture. Modern engineers examining proximity fuse specifications occasionally express disbelief that the devices worked at all. The design pushed vacuum tube technology far beyond what experts in 1940 considered possible. Yet they worked reliably enough that military commanders trusted their ships and their lives to them. The failure rate for proximity fuses delivered to combat units measured below 2%. Remarkable reliability for such complex devices produced in such enormous quantities. The secrecy surrounding the program produced its own challenges. Factory workers assembling components had no idea their work contributed to one of the war's decisive weapons. They thought they were building improved mechanical fuses, precise but not revolutionary. Maintaining this deception across dozens of facilities employing thousands of workers required elaborate security theatre, with different production lines building incompatible components and fine assembly restricted to heavily guarded facilities. The security measures proved effective. German and Japanese intelligence services never penetrated the proximity fuse program. They observed the effects in combat, analyzed wreckage from downed aircraft, and speculated about American advances in anti-aircraft technology. But they never determined the fuse's operating principle, never discovered the radio frequency detection system, never learned about the ruggedized vacuum tubes. The secret held throughout the war and for several years afterward. Declassification began gradually after 1945. The Navy released limited information about variable time fuses in late 1946, acknowledging their use in anti-aircraft applications. Full technical details remained classified until 1952, by which point the technology had evolved beyond wartime designs. The principle, however, remained relevant. Modern proximity fuses use solid-state electronics and 2000 CON, digital signal processing. But the core concept, a projectile that senses its target and detonates at optimal range, remains unchanged. The proximity fuse influenced post-war weapons development across multiple domains. Surface-to-air missiles adopted proximity fuses as standard equipment. Artillery shells continued using proximity fuses for anti-personnel applications. Even small arms ammunition experimented with proximity detonation, though miniaturization challenges prevented practical implementation. The idea that weapons should sense their targets rather than relying on precise aim became embedded in military thinking. The cost-benefit analysis remains striking. The entire proximity fuse program, from initial research through wartime production, cost approximately $1 billion in 1940s currency. For that investment, the United States gained technology that reduced anti-aircraft ammunition expenditure by 75%, while increasing effectiveness several-fold. Ships survived that would have sunk. Aircraft were destroyed that would have escaped. Soldiers lived who would have died under conventional artillery. Quantifying lives saved proves impossible. How many sailors survived because their ship's anti-aircraft fire stopped a kamikaze at 500 yards instead of allowing it to crash into the superstructure? How many infantry survived because proximity-fused artillery destroyed attacking German troops before they closed to assault range? The numbers exist somewhere in the realm of thousands, possibly tens of thousands, but precise accounting defies any methodology. The technological lineage extends to contemporary weapons. The AIM-9X Sidewinder air-to-air missile uses an active radar proximity fuse. The Patriot air defense system employs proximity fuses in its interceptor missiles. Artillery shells fired by modern howitzers can be fused for airburst detonation using proximity sensors. Even some small arms grenades use time delay, proximity fuses for airburst effects. The principle, proven in 1942, remains relevant 80 years later. Modern military historians studying the Pacific War's trajectory often identify the proximity fuse as one of several technologies that shifted strategic balance decisively in America's favor. Radar-enabled detection, fighters provided interception, but proximity fuses made defensive fire effective enough that Japanese air attacks, even kamikaze attacks flown by pilots willing to die, could be stopped reliably. The combination created a defensive capability that made American fleet operations sustainable, despite facing an enemy who'd pioneered carrier aviation and perfected it through years of combat experience. The program's success rested on several factors beyond pure engineering brilliance. Adequate funding allowed parallel development paths and rapid prototyping. Close cooperation between military requirements officers and civilian researchers ensured the device addressed actual combat needs rather than theoretical capabilities. Ruthless quality control prevented defective units from reaching combat where failures would cost lives. And critically, Industrial scaling allowed production to match demand, ensuring every ship that needed proximity fuses received adequate supplies. Compare this to German wonder weapons programs that consumed similar resources but delivered minimal combat value. The V-2 rocket killed approximately 9,000 people while costing billions of Reichsmarks and consuming scarce resources Germany desperately needed elsewhere. The proximity fuse cost comparable amounts but shifted the strategic balance of entire campaigns. One program represented technological capability divorced from military utility. The other represented engineering focused ruthlessly on solving specific combat problems. The proximity fuse also demonstrated American advantages in electronics, manufacturing, and precision engineering. Building 22 million complex electronic devices required industrial infrastructure, skilled workforce, and quality control processes that Axis powers couldn't match. Germany produced excellent scientists and brilliant prototype weapons, but Germany couldn't manufacture sophisticated electronics at American scale, while simultaneously producing tanks, aircraft, ammunition, and everything else required for multi-front war. Japan's situation was even more constrained. Japanese electronics industry in 1942 barely existed in forms that could support proximity fuse development. Japanese radar technology lagged years behind American and British systems. The idea of miniaturizing radar into a shell-mounted package would have seemed fantasy to Japanese engineers who struggled to build functional ship-based radar sets. The technological gap wasn't just wide, it was effectively unbridgeable given wartime constraints. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.